Okay. Oh, this is the wrong place. Okay. Okay, so questions before we get started? Yeah.
Is there any way you can do some of the math problems because I'm asking other students to make something on the issue and I hope people want to like the office to do it and maybe you can put some time during possible.
Why didn't you want to know?
I don't know, like I'm a busy schedule.
Okay.
So I work 12-hour shifts. I'm taking 4 courses.
Yeah.
And taking extra days and inconvenience and also coming from my life.
So we can do it by Zoom. We can do it by Zoom.
But I just feel like if another person has that issue, like there's gotta be other students that are probably having issues with the math problem.
Sure. Okay, so for today, we're going to do a little bit math together. Not because I anticipated that question, just because that's about as far as we're going to get in math. Okay. And we're going to do like ratios of math, and that's about it. And the rest of it will be very you gotta rely on some intuition, like hot stuff goes up, heavy things switch. Okay. And most other than that, you won't see a lot more math. Okay. So if after today you still need a little bit of help or you want to see some more stuff, just let me know via Slack or via email or whatever, and I'll just work it in more. Right. Did you also have a question? No. Yeah. Okay. What's that? Oh yeah. Okay. So we're gonna get to that. So you already saw that this morning. There's some very unusual phenomenon. There's just like water like from the sky or something. So if that's happening, we can't do telescope observing. I put on the calendar already that we're going to do a training for volunteers for the observatory. And so you're obviously welcome to do that. Is there a way to make this? Not normally like that, right? Okay. So we're going to do a telescope training for the at the observatory. There's lots of files. We'll talk about this in a few minutes. Like if you can't see the sky, don't come. Right? You can't see them. Okay. Okay. So we're going to go back to that in a few seconds. So yesterday I went to see Lil Wayne at the 2K premiere. And I was like trying to figure out how to work that into a conversation. It's like, obviously that's really fun. So what I did is I found they were giving away swag. So this is a 2K bag. And do people like 2K? NBA 2K? Does anyone know what that is? Raise your hands. Okay, so there we go, raising your hands. And so in addition to that, there's like a hat and like a water bottle and a water bottle and the games for Xbox. So to incentivize participation, okay, people will win them today. Okay, so y'all came for the best day. Okay, questions before we get started? So the way this will work, we'll raise our hands and I'll call on you. If you've won once, you can't win again. That's rude. The first person to win gets to pick, so on and so forth. We'll deal them out at the end, okay? Okay? There we go. Okay, so what are we looking at here? Yeah, an astronaut having a really, really bad day. So this is like a picture from Gravity, if you've seen that film, where they're up in space fixing the space station and some stuff hits them and then they're like floating in space, no life support, nothing to do, and you have to somehow get home. This would be terrifying. We're going to talk about how things move in space. We're going to talk about why we orbit, and as mentioned, let's talk a little bit about the math. The first part's going to be a little tricky. We're going to talk about how this gravitational force works. We're going to write it down. We're going to finish up that lecture tutorial. And then hopefully we have enough time to get into the stuff that I actually care about, which is looking at planets because they're really cool. Questions? Okay. So this was the universal law of gravity again. Just to refresh people's memory. On the left-hand side, you have one mass. Doesn't necessarily have to be bigger. Doesn't matter how you set it up. The other side, you have the other mass. They are attracting one another. There's a force between them. The force is described by this. You can ignore this for all intents and purposes, as we'll talk about briefly. And it's just the product of the two masses divided by the distance between them squared. Okay? You don't have any intuition for that? That's totally okay. That's what we're going to build today. Okay, that's the big G. So let's go to this question here. We've done this one. We're going to see the same one here. Okay, so I want you to put your fist up. Think about this answer for a second. So the question is the gravitational force the Earth exerts on you larger, smaller, or the same as the force you exert on it? So show me with your fist when you're ready. You don't play, you can't win. Does that make sense? People's hands go up. Okay, 3, 2, 1. Okay, I see a lot of 3s, some 1s. Does anyone want to defend their answer? Raise your hand if you want to defend your answer. The first prize will be there. Yeah.
So if you and Earth have mass, it's the mass of Earth times the mass of you divided by the distance between them. It's the same either way.
So does the order of the M's matter there?
No, it doesn't.
Good. Ding, ding, ding. Which would you like?
Water ball.
Water bottle. I won't throw it, but that'll match with someone. I'm not necessarily good at it. Okay. So the same equation applies to M standing on M, or M2 standing on M1. So for example, here we have a force. Person who controls the force the best, obviously, Lord Vader. So the everyone knows who that is, right? Yeah. So D is the distance between the centers. So we're going to imagine, for the purposes of talking about gravity, that everything is really a point. Of course, it's not, but for the purposes of what we're thinking about here, we're really pulled towards the center of the Earth, right? So we're standing on the Earth. We're not pulled off to the side, we're pulled directly down, okay? And the distance is just the distance to the surface. It's exaggerated as though he's large. Of course, the Vader would never be that large, okay? So let's put him on a ladder. It's a fantastically large ladder. It's going to be twice as big as the radius of the Earth. And my question is, how does that force on Darth Vader change? Okay, the only thing that I'm changing here is R to 2R, but I want to take a ratio of those forces. Okay, so I don't actually want to compute the number. In fact, the number is going to hurt me, but the ratios are nice. Like you say, well, when I was 5 years old, I was half as tall. That's intuitive, right? Let's make a ratio. Anyone have a problem with this? Does anyone want to make an educated guess? Raise your hand if you want to make an educated guess. First chance to win a prize? I guess they weren't very cool prizes. Okay, so let's solve it then. This is the ratio the mathematical way. So you have this one here. You just write the equation. When he's at the bottom, we're going to put it here. And you can say that the distance is the radius here. E is R. Okay? The masses, they're just there. We're not going to do anything to them. Okay? When he's at the top, you have the distance to the top. And you can write that here as twice the radius. So the distance to the top is twice the radius. But I have to square that quantity. So if I'm doing the square here, b squared, the square of a product is the same as the product of the square. That means that I can take the square here and I can distribute it to each of those. So that becomes 2 squared times r squared. What's 2 squared? To raise your hand, you could have gotten a prize. Okay, that's 4. Do we see anything yet? Yeah, go ahead.
It's like a little bit distance, like weakens the gravity force.
Yeah, weaken the gravity force. That's correct. That's what we're going to demonstrate. Yeah. And here you can see a lot of the same letters. So what if I take a ratio of this one compared to this one? Okay. I can just divide them, the top by the bottom. And my favorite thing to do is to just cancel out everything that I don't need. I've got G on the top, I've got G at the bottom, get rid of it. I've got M at the top, I've got M at the bottom, get rid of it. I've got R squared on the bottom and R squared on the bottom, get rid of it. So what do I have on the top now and what do I have on the bottom? Hand and prize. Yeah.
So you got 1/4 of F top and one at the bottom.
Correct. You folks see that? I got rid of all of that with all of that. I got rid of the R squared with the R squared. So I had a 1/4 left on top and 1/1, which is 1 on the bottom. What would you like to have?
The half.
The half. Okay. Questions? Comments? Concerns? Yeah.
Gravity all forward, but it's still falling. So what does that mean? The farther you are from the surface, the less.
So as you move, like what this is attempting to show is that the force of gravity is indeed weaker as you move away from the surface. So for example, if I were standing at sea level versus standing at the top of Mount Everest, you can do a calculation. You can figure out how much less gravity is pulling you down the surface. So what you're saying is almost right, except for when you're in orbit, you're in a special type of motion because you and everything around you is falling at the same rate. Right? And we'll talk about the orbiting in a few seconds. So when you have something like a ball or something that you drop, it just stays there. Doesn't feel any gravitational force at all. But the force pulling you, you just happen to be moving out of the way of the place that you would fall into. Does that make sense? Other questions? Okay. So you all started this, right? Let's bust them back out. You're going to get into groups of 2. You were in the same group or sitting next to the person you're sitting next to. You can work with that person or you can make a new friend. I also have other versions if you need a new version. And we're going to do the second and third sections, I think. Yeah, force distance relationship. Okay. Yeah. Oh, yeah. Yeah. Yeah, and oh, I was also asked today to put them all online. So if you don't have a copy or you didn't remember one or you missed one, you'll get a blank one that'll be on Canvas that you can reference. Thank you. Yeah. Did you need one? Oh, it's a good thing I ran back. You want to? Yeah. Okay. It's my last one. I'm trying to partner. I'm being a group of 2 as well. We keep every note in favor. So for the first section, we already did this one. We weren't able to do it for 20 years. You want to actually, what was your name again? You want to work together? Yeah. part 2.
So.
There's a. Yeah. How many do you have? So I would say maybe shuffle around to smaller. Okay. Like you don't really have. It's okay. But like if you're writing, all the writing, they'll either back and forth, maybe otherwise it looks like one person and I don't see. Sure, but are you okay? So you have 6 people. So okay, are you guys all happy? The 2 groups of 3? Okay. So if the exam has a question on this exact part, it's still fine, right? Yeah. The mass directly in proportion. Relation one of them. Or the way you get from the weaker, larger first, larger mass. I need a little bit more. Yeah, but this is easily.
Yeah, and they could one, one, that's one.
On the dragon. Yeah.
And then I told them.
So the board is on. Oh, I did say that on that. No, but I see it. You didn't get that. Made the mountain stage was tiny. Not a requirement, but it's not. Right, remember this part here.
Okay, so try to wrap up what you've done so far. We're gonna answer questions, continue. If you haven't finished, that's totally okay. You can see if there's time at the end. Otherwise, you can work on it individually. Y'all done? Oh. Okay. Okay, folks. So let's put a little break in it, and we're gonna talk about these questions. And then if we have, if you have to come back to it later, that's fine. And we can ask questions in either office hours or online or whatever. Okay, so this is going to use the information that we've just attempted to digest. It's going to be another question that you will eventually win something for. Okay, if you have won something already, you can't win again. I'm sorry. So the question is, how strong would gravity be at the surface if the Earth was replaced by a styrofoam ball, the same mass, but 10 times the radius? Is it A, 100 times stronger, B, 10 times stronger, C, unchanged, D, 10 times weaker, E, 100 times weaker? Okay, and to win here, you're going to raise your hand and you're going to have to explain your answer. Was that a hint? Yeah? What do you think it is? That doesn't matter. That is not how we do science. We give whatever answer we have, and then we figure out if it's right. You might still win. Mm-hmm. So even though the size of the name, if it was still bigger, then So, okay, so the same mass, right? So the m's are remaining unchanged, but 10 times the radius. Is that what you're saying? So it's right that it's lighter in density, same mass. But how does it affect the force? We want to swoop? Yeah. Final answer?
Yeah, I think that's
Yeah, so that's unchanged. Anyone, what do you think? Okay, anyone not camp free? Yeah. Yeah.
Oh, I feel like gravity would kind of be weaker because, like, with the knowing, like, that like planets or things that are like smaller, they have a weaker gravitational force, like they will jump higher.
Okay, so that's the moon, which is smaller. So that's the smaller mass. That's if I were to change one of these. So it's not bad reasoning, right? But what part is changing here in this equation? Yeah. The radius is changing. By how much? 10. And that square is? Okay. So we don't think it's this. We don't think it's this, and we don't think it's that, because that's 0 and 10s. So now we have a 50-50. We can flip a coin and we can win. Yeah. You think it's E? Why do you think that? Mm-hmm. So you think it's E because it would pull more on the Earth? So the mass is the same, and D got larger, but it's in the denominator. The force went down. So it was 100 times weaker. And that's the correct. Okay, which would you like? The bottle? Yeah. Okay, so let's do that together. Okay. So what variable changes when, wait, did I go the right way? Yeah. All right, so let's change the distance to 10R. Okay, what variable changes? G is a constant, we hate it, we throw it out. M doesn't change. The mass of Darth Vader doesn't change, and it's only D changing as we stand. So it's D going up by 10. D squared is 100, but it's in the denominator, so it's down by 100. Weaker by 100. Okay, so the force then must be weaker by 100. So this is why, interestingly enough, when we think of something like Jupiter, which is super large, but also massive, it's maybe not immediately obvious whether or not the gravity at the surface would be larger, smaller, or the same as here on Earth. That's a problem we'll do later. Okay? Questions about this process? Did I lose everyone? Okay. So far we've only been talking about the force. We experience forces, right? That being held onto the ground, these are all forces. What about acceleration? So for example, how fast does a cabbage fall towards the Earth? That's a question we can answer. And how fast does the Earth fall towards the cabbage? Does that make any sense? It makes perfect sense. Who said that? It's the correct answer, but maybe not intuitively. Okay, so as I jump up, okay, I push the Earth down. It pushes me up. And then as I fall back down, I also pull it up pretty strong. So how does that work? Works like this. Here's the acceleration due to Earth's gravity. We already saw that the mass of the, I don't know how to make a cabbage, but whatever, this is a circle that's green. Compared to the distance to the center of the earth, right? We also know that we can describe this in terms of F equals ma. That was Newton's second law that said that there's a relationship between the acceleration, the force, and the mass. So if you have a force acting on an object, I forgot my baseball, God damn it. The bigger objects require more force. So if this has more mass than this, then this can be moved more easily, less force than this, right? Okay. But I can rearrange this as we saw in that slide, or I could talk about the accelerations just being the forces divided by the mass. Okay. And I really love canceling stuff. So I want to look at the accelerations on a piece of cabbage. I have the force up here on the cabbage. That's just the force we just used. G, mass of the earth, mass of the cabbage over the radius of the earth squared. And which one is this, by the way? What's that? Earth. In this particular example, we're looking at the force on the cabbage. This was the force on the cabbage. This is the acceleration on the cabbage, and this would be the mass of the cabbage. Okay. So I really like canceling stuff. I see mass of the cabbage twice. So what am I going to do? Cancel. Oh, shit. So this one is going to disappear, and this one's going to disappear. Okay, so we're going to win more things. Okay. Why do a cabbage and the grape hit the ground at the same time? Is it because A, the masses of the cabbage and the grape were tiny compared to the masses of the earth? Is it B, the mass of the falling object doesn't matter? Is it C, they actually fell at slightly different speeds, but over that small distance, it wasn't noticeable? Okay, if you're ready, put your fist up, so we're going to see which one this is. Can't win if you don't play. Okay, 3, 2, 1. Okay, I got a lot of people who just decided not to play. Okay, there we go. Oh, interesting. All right, does anyone want to defend their answer? Yeah.
I think it's because it's kind of like that saying, the bigger they are, the harder they fall. So obviously the cabbage would fall much more quickly. Since we would have the same the same small distance, it wasn't that easy.
Okay. I like the reasoning. It has an intuitive feel to it. It's not actually correct. I'm sorry. You want to try a different one? Let's go back a second. Yeah, so the cabbage here cancels with the cabbage there. Does that help us? It's almost like they're really. What was that? That's very interesting. Is that your final answer? That's correct. The mass does not matter. The reason they fall at the same rate is the object that's falling falls at the same, because it's subjected to the same acceleration. Its mass doesn't show up here, right? So the mass of the earth is the only one that shows up there, which is why I don't feel any force gravitationally from this clicker, right? The acceleration I feel towards this clicker is quite small because the mass is quite small. And that's your sort of everyday life understanding of like, well, I'm not just thrown into my desk every once in a while. So the acceleration of everything falling together is only dependent on the mass of the earth. Now the force is dependent on the product but the acceleration is not. Okay, we experience accelerations, we use forces to get stuff done. Does that make sense? So which would you like?
You can sit down and see what that is today.
Oh, does anyone want a free gift? Would you like one for participating?
Forward.
Yeah, which one do you want? The game? Surprised no one took the bet. Glad I didn't hit him. I guess I should have said I was throwing it, and I didn't throw any other ones. Okay. Okay, so here's that acceleration due to gravity. There's me canceling them out. And we can just see that the acceleration of the cabbage due to the Earth is only a product of the mass of the Earth and divided by the radius of the Earth. Okay? Okay. And it turns out if you put all those numbers in, that's how we got that 10 meters per second squared. And we were talking about tossing something off of a building and it gains 10 meters per second. Yeah.
So it because it's a lot from the front.
Yeah.
Does that mean that we're in a problem?
So that's a very good question. So currently we're on the Earth, right? And the reason that we are going around the sun is because of the gravitational force between the Earth and the sun. So if we were to leave spaceship Earth, like we saw at the beginning with that picture of the girl unbound, then the question is, what would we be doing? Well, we would just be free falling around the sun, right? And there are rocks that do this, lead very sad lives. No one hangs out with them. Does that make sense? Okay. And this one is an independent value. So you can calculate this for every planet. So if we calculate it, say, for the moon, we'll see that the moon's mass is smaller and the radius is smaller. So you might think, that's going to matter a little bit. It turns out that you have about a sixth of this speed. That's why everyone looks funny. You jump around. Everything works good. And also, I should have put the picture here. Did I do it? Oh, there's a video. It's a better one. Of course, astronauts are like, test pilots and whatever, and they do basically anything they want. So they decide they're going to bring golf club up to the moon, and they just like cheat off to see how far they could drive because the gravity's reduced, so they could go like 700 yards. It's pretty cool. Let's do that calculation. That's okay. I'll find that video and I'll post it because it's actually really funny. So this is the acceleration on the moon, and we can do that by looking at the mass of the planet and the radius of the planet here. We can compare it to the Earth, right? Because I don't actually want to calculate real numbers. I just want to know what the fraction is compared to something I know. So if the fraction was 1, if it had the same, then I would feel like it was the same amount, right? Okay. And I can just group these up. I get rid of the G's because I hate the G's. And here are the M's grouped together. Right here. And then the R squared grouped together. And sure enough, I can distribute these R squared. They both had an R squared, but I can use the parentheses around both of them. Right? The product of A and B is the same as the product of B and A. So I'm running that. And then I know these fractions. So the mass of the moon and the mass of the Earth. Well, the mass of the Earth is 81 times the mass of the moon. So I just put that in right there. And the radius of the Earth is 3.7 times larger than the radius of the moon. I put that in there. And it comes out to about a sixth. That's as complicated as the math will get, I promise. Questions, comments, concerns? Okay. How much does the Earth accelerate due to the cabbage? A lot or a little? Yes, a little. In fact, we barely see this at all. So there the mass of the Earth gets cut out. And the acceleration of the Earth due to the cabbage, like we talked about with my clicker, is very little. Okay. If I calculate it, I know I said I would never do that, but I did it for you. It's tiny. This is 10 to the minus 24. This type of number, your brain can't even really conceptualize properly. Okay. Fine. Imperceptible. Okay. So your point about orbiting, are any questions before we move on to this? So how fast do things orbit? Someone have like an intuitive sense and say miles per hour? Like 5 miles an hour, and larger, smaller. Sorry, not in the conversion. Like what is the like rough numbers? What would you guess? Is it like hundreds? Yeah.
What thousand?
Thousands. People like that guess? Thousands? That seems nice. Thousands of miles an hour? Yeah. Okay. So somewhere in between there, maybe? I don't want to make you guys fight. We're gonna figure that one out. Okay. Okay, so orbiters, so planets, for example, they're constantly trying to get away. Newton's first law of motion says stuff in motion remains in motion. So if you started moving, right, the only reason why you're changing your motion is because a force is acting on you. In this case, that force is gravity. So gravity keeps turning the planet. Now there is no air friction in space. So as it's moving, the direction is only changing and it's not slowing down. If it were slowing down, that would suck. We would burn up into the sun. Okay? So gravity is only changing the direction and it's not changing the speed. Okay, and we can use these laws that we just calculated to find out how fast. It's like that. You're not going to have to calculate that or derive it. I'm not going to show you the derivation. Okay, but it has only 3 things. The speed in a circular orbit is just the mass of the thing that you're orbiting, for example, the sun or the Earth, right? So if we want to calculate this for us in space, detached from our space station, we would put in the mass of the Earth and the distance above the Earth, right, from the center. So if we were floating 400 kilometers above the surface, we would add that to the radius, and I would be moving very lightly. Okay? Okay. All right, 2 new things. An astronaut and a camera are floating outside the space shuttle. Which moves the fastest? Real picture. Shuttle has the greatest speed due to the greatest mass. B, the astronaut experienced the greatest deceleration since they just exited the space shuttle. C, the camera's speed is fastest due to lowest mass. Or D, astronaut, shuttle, and camera all have the same orbital speed. First up when you're ready. Three, 2, 1. Okay. If we go backwards here, this is the speed here. This constant, we don't care about G. I should have actually deleted it from the slide. Mass of the orbitee over the distance away that they are orbiting. Okay. Does anyone want to defend their answer? Did you win? Okay, go ahead.
I think D.
Why did you pick D?
Because I mean, out there, I mean, they would have been with it. They should be.
Can't tell if he's moving.
They should be moving at the same speed. Because if they don't move at the same speed, then probably like depart away from the.
So that's a very good instinctive answer, right? You'd be like, you'd be pulled away, right? But we can be slightly more quantitative. We can use something that we just learned. You want to modify?
Oh yeah, it's like you said last It's like basically
Uh-huh.
and motion state.
Sorry. Okay. Okay. I like that explanation, but it's not exactly what I'm looking for. Okay. Did you want to?
Does that mean that I'm a P?
I don't know. Do you want to defend a different one?
Say A, just because the last line.
Yeah. Okay, so that's a good question. So whose mass is this? The what? The orbit T. Yeah, the thing that's being orbited. Sorry, but you had your hand up second.
Yeah, I was thinking, because I was saying the order, but wouldn't it all be the same thing, considering that in space, everything's like slower, so then if the order speed is all the same, so then space slower the time, and that's not the
So I think that some people are arguing for D here, right? And I'm just looking for a specific explanation from this one that supports that. You already won, right? Okay. Do you have a separate question?
Yeah, so the orbiting question.
Yes, the orbity here would be Earth. Yeah. They're all the same distance from the Earth. Is the mass of the Earth different for any of them? No. Is this different for any of them? No. So this must be the same. So you're both right. Okay. But in fact, it was D. They all have the same orbital speed, but it's because they're at the same distance. And the Earth has the same mass for all of them. Okay, so they all float together at the same distance. Which would you like? The back. So therefore, all orbiters have the same orbital speed. Okay, we're running out of time. Orbital speed for satellites around the Earth is large. It's about 18,000 miles per hour. So that's kind of hard to conceptualize. I don't like to think of it that way. I think of it like 8 kilometers per second. If you've ever driven a kilometer, you know that it's like roughly like a mile. I don't know. Who knows what those numbers are? But imagine going a mile a second. That would be very quick. And in fact, this is why when you see something re-entering the Earth's atmosphere, it glows hot red. That's because it's moving at 18,000 miles an hour and it's burning. Yeah. Well, when it enters, it'll slow down. That's what causes it to heat up. But right before it enters, it's going very fast. Yeah. Yeah, sometimes they explode. We'll talk about that soon. Okay, questions about this? Okay. It turns out, and I'm not going to show you, that the escape velocity, the speed necessary to leave, is almost exactly like the orbital one. You just add a little 2. Square root of 2 is like 1.2 something. So it's like 20% more. So once you get into orbit, you're very close to just being able to leave and go to the next planet if you want to. You just need 20% more speed. Okay. So the orbital distance, I should have said, yeah, this will be fine. This is circular orbit, is 8 kilometers per second or 18,000 miles an hour. And the escape velocity to get away from the Earth forever is 25,000 miles per hour. Okay, this is all we're going to do with orbiting. Any questions before we move on? Okay, and then I'm really briefly going to talk about the idea of conservation. So this is an example of what's called Newton's cradle. And you have all of these balls on little like strings, and then you pull one back and it hits, and it click, makes this other one click up, and then come back down, hit this one bounces up, and it's sort of an annoying little toy for, you know, people's offices. You ever seen that? Quack, quack, quack. Yeah. Okay. I can get a video of that if we want. So we want to think about two sort of questions really quickly. How does an ice skater spin? And where does energy come from? Can it be lost? Can it be created? How does an ice skater spin? This will be my first question. Yeah.
The force when turning into a direction.
Yeah, so I just want a description of like, what are they doing to spin?
They open their hands, so the spin, and they have a hand open, slower motion than closing, right?
That's correct. You can open and close your hands in order to modulate your speed. So
It's the same as like when you're going on the swing, when you close your legs, you
yes, that's actually true as well. That's a very good example. Okay, so this is something called, ready to go? This is called conservation of angular momentum. Sorry, that's my last gift. I'll try and bring something else at some point. So what does this mean? You don't need to memorize this. In fact, I will be shocked if you do. I don't want to spend a lot of time here. The basic idea being that this is a conserved quantity. You don't create and you don't lose angular momentum. You just change it. So the ice skater is spinning like this, and as they pull their arms in, they spin faster. Radius goes down, velocity goes up, mass stays the same. Okay. There was going to be a question here, but I'm not going to do it. It just looks like that. It's fairly straightforward. This will be important later on, so we'll refresh this topic, but I'm just introducing it here. This one is the more important one for what we're about to talk about, what we'll talk about on Tuesday. Okay. Conservation of energy. You cannot create energy from nothing. Okay. All energy is accounted for, and it just moves between different forms. So as you go up this hill, you're working really hard to get up the hill, and then you can go down. It's really fun, air flowing by you. You are changing from potential stored in your legs. Maybe you had a protein bar before lunch, and then you got up to the hill and you had all this stored potential and the fact that you're at the top of the hill, and then you just roll down, and that turns into speed again. Okay. So that's energy in the form of kinetic. Potential, you're stopped, no longer moving. And then energy out, you're moving again, and you're getting rid of that energy. Okay. This is about as far as we need to keep this idea, because we're basically just going to use it to motivate both the dynamics when we're talking about how things sort of squish together, but also like biology. So we're all alive because of the sun. Sun creates grass, makes cow. Maybe you don't participate in cow, but some people participate in cow. And then we use cow product to run uphill. Okay. If you think about something like dinosaur, and that is what you use to get to work or to keep your house warm or cold, depending on how you look at it, that dinosaur ate sunlight. Okay, so that step there after eating some vegetation or eating something that ate vegetation. Okay. Okay. It's never created, it's only transferred between forms. And this is potentially the most important part. So here I can take something like rotational energy, and you can do this yourself. You take your hands, you do this. What happens? What? It gets warm. It gets really warm first, right? So that's what's happening here. They are spinning. This is called a friction weld. So you're taking rotational energy or motion, and you're turning it into heat. Heat is a form of energy. Okay. This is another example. They want to take waves, turn it into electricity. Okay. So this is the section on physics. That's it. Is everyone happy? No more physics. Yeah, boo. Okay? Everything from here on will be fun because what we're going to do, now of course I'm gonna lie about this because we're gonna do it for like 4 weeks and then you're gonna have to learn more physics. So for this part, we're gonna be really just looking at pictures and we're going to try and identify some features that we see on different bodies. And then we're going to try and work backwards towards what causes those. Now, of course, I already know the answer. So I'm going to kind of guide you through that. I want you to like participate like we did today, even if you don't have anything that you're trying to win. I think just because they'll be cool. So here we're talking about this. I don't know if there's going to be clouds out. You can check when we leave. I have like 5-6 minutes. Let me show you some pictures. That'll make you want to come back on Tuesday. Okay, so we're going to talk about planetary geology. And the questions that we're going to ask here, this is one of my favorites. What's happening here? Volcano. I hear that. And what's happening in there? Lightning. Is this a real picture? Yes, this is absolutely a real picture. This happens all the time. Very fine particles coming out, and they're electrically charged, and then the electricity goes between them. This is magma, lava. This came from inside the Earth, and it came out. We're going to find out why. And then those are stars. No one cares about those. Okay. So the first question is, why do the planets look so different? We're going to try and answer this one. We're going to ask why does life have Earth, but apparently no other planet that we are aware of. And are there processes that occur on all planets, or is all of this just random shit, right? That's one of the major questions. So here's what the planets look like. And I'm just going to explain what the planets are, and I want you to tell me what types of features you're seeing by raising your hand. This is Mercury, Venus, Earth, the Moon, and Mars. And yes, I put the Moon in there. Don't get upset. What types of things do you see? Yeah.
Mercury has a lot of craters on it.
Mercury has a lot of craters, okay? So we have some circles, a lot of circles. Cool. Yeah. Venus looks hot. Okay, so you associate this color with hot. Okay. Okay. Yeah. Yeah. So it looks like there's these like trails here. Maybe there's like trail runners, people doing 5Ks or it's actually funny, but it's not funny. So when they first looked at the reason that we think there are Martians is because they looked with a telescope, it wasn't a very good telescope, and they saw shit like that. And they're like, there's canals, like full societies. There must be people on Mars. And they were wrong. It was just this. Very sad. Anything else you see? Yeah. Very good point. Mercury and the Moon look very similar. I could have tricked you to show you the Moon up here. You wouldn't even know, right? Anything else? Yeah.
The Earth is brown. It's brown.
Brown. Yeah, the Earth is brown. That's one of my favorite planets. It also has this other really cool color that I like. Blue. It's the only blue one that I see here. That's fun because I'm thirsty a lot. The brown is vegetation. Anything else we see? So we're seeing these parts too. Anything that you're noticing about these? Is this one hot? That looked hot, you think? But this one looked hot. What's the difference? Okay, we'll think about that in a little while.
Water, ice.
You see water and ice where? Here? On Mars? Where? Okay. Yeah, so it doesn't look like there's flowing water here, right? Looks like that's all dried up. Okay. So here are the things that I noticed. Mercury and the Moon, we can kind of pair them together. They looked really cratered. I think a lot of people said that. There were some volcanic plains, a few cliffs and ridges. Venus looked like there was bizarre bulges, volcanoes, but almost no craters. Did you see that? There are these like little dark spots, but not like a bunch of circles everywhere. And if I look at the Earth, I also don't see a bunch of craters. When you're driving around, you don't just see craters, do you? Whereas you can imagine if you're driving around on the moon or Mercury, you probably bump into tons of them. Right? Mars has some, but they kind of even look weird. Almost like they're not very sick. These ones here are like straight circles. Boom. This one's like weird. I don't see any volcanoes on here, but I do know that there are volcanoes on Earth, so I'm not going to ignore that. I didn't see any volcanoes here. I don't see any volcanoes in this picture, but there are massive volcanoes on Mars. Okay. Anything we're missing here? Volcanoes and canyons, dry riverbeds, we said that. Most of the above plus liquid water and not much grading. So we did all of it. That was great. Good job, guys. Okay, so we're going to have observing. If there is no clouds, you're welcome to come. Not a requirement. And then we're going to do it again next week. That'll be the open house winner. Okay, thank you.